Okay, now if you this is the presentation, we already saw this presentation. We talked about the autoregressive models, and we got up to this point here where we say that given that was the last thing we covered. Let's see, yeah, the last thing we covered in the autoregressive presentation was that the representation for an autoregressive process, which is stationary, as a linear combination of white noise, okay? At time t, t minus 1, t minus 2, etc. And we talked about stationarity, that depends on the conditions that we have on the p parameters for the autoregressive order p model, okay? Now, we saw a couple of autocorrelation functions for autoregressive series. And it's not clear from the autocorrelation function if that is a pure autoregressive model and which order that autoregressive model is. To be able to determine the order of an autoregressive model, we are going to introduce something that's called the partial autocorrelation function. Okay, partial autocorrelation function will help us determine the order of an autoregressive model. This is a function that is similar to if you already took regression analysis, when you do regression on one variable, given that you already have another one in the regression equation. So let's start with a simple AR1 process. In this simple AR1 process, remember we have ZT is phi, which is our parameter, times ZT minus 1 plus AT. Remember that in the AR1, we already saw that the autocorrelations behave for the AR1, they behave as phi, which is this parameter, raised to the absolute value of k. So if the process is stationary, phi is going to be less than 1, and therefore this autocorrelation function will have an exponential decay towards 0. We saw that when we talked about the AR1 process. Now, suppose we want to quantify how much ZT depends on CT minus 2, okay? This model relates ZT with ZT minus 1 because it's an AR1 process. However, just imagine that it wasn't an AR1 process, then it was an AR2 process. And there will be a relationship between ZT and ZT minus 2, okay? Independent of the fact that we already have ZT minus 1. So to be able to know, for example, if it's an AR2 process, then we would want to know how much influence ZT minus 2 has on ZT after I account for CT minus 1. And that's what we're gonna compute. This is by analogy with regression models when we add a variable and want to see how much an additional variable contributes to the regression equation, given that the other variable is it's already there, let's say. That thing that we estimate in regression is the equivalent of this, what we're calling the partial autocorrelation. We call it partial autocorrelation, and we'll denote this, or initially we'll simplify the notation, but we'll denote this partial autocorrelation as rho of 0.2.1, and reading this as the autocorrelation between ZT and ZT minus 2, given that I already have CT minus 1 in the model, okay? So given that I already have ZT minus 1, what's the autocorrelation between CT and CT minus 2? If that autocorrelation is strong, then definitely we would need ZT minus 2 in the model, okay? And that's the partial autocorrelation. The way we compute the partial autocorrelation of rho 0.2 given 1 is we take the correlation between ZT and CT minus 2, ZT and CT minus 2. Then we subtract the correlation between CT minus 1 and CT Okay, so rho 02 is the autocorrelation of ZT and ZT minus 2. The rho 01 will be the autocorrelation between this one here, rho 01. I'll put it down, I'll erase it now. Rho 01 is measuring the autocorrelation between ZT and CT minus 1. And rho 12 is the autocorrelation between CT minus 1 and CT minus 2. Okay, so we take the autocorrelation between ZT and CT minus 2, subtract the product of the autocorrelations between ZT minus 1 and ZT minus 2, and standardize that by the square root of 1 minus rho 01 squared times 1 minus rho 12 squared, 12 squared. So in either case, these are autocorrelations 1 lag apart, and this is an autocorrelation 2 lags apart. So this is called the partial autocorrelation between ZT and ZT minus 2. Okay, that's the partial autocorrelation. And that's a measure of how much ZT depends on ZT minus 2, considering that, given that ZT minus 1 is already there in the model. Okay. Now, ZT rho 02 is then the autocorrelation between ZT and ZT minus 2, and rho 01 and rho 12 denote the correlation between CT minus 1 and CT minus 2 and CT minus 1. And that what I just wrote. Now, it follows then that if a model is really an AR1 model, then the autocorrelation between CT and CT minus 2 given ZT minus 1, let's say, is going to be 0. Because this, if this is in fact the true model, if this is the true model, I do not have dependency on CT minus 2. So the autocorrelation between CT and CT minus 2 would be 0. Okay. In fact, all partial autocorrelations that exclude CT minus 1 will be 0. Okay, for an AR1 model, because the AR1 only involves CT minus 1. So if I compute any partial autocorrelation that excludes CT minus 1, that partial autocorrelation is going to be 0. Okay, for every other lag. Okay, because I'm excluding the only variable that helps me predict ZT. Now let us consider an AR2 model. An AR2 model is ZT equals to phi 1 CT minus 1, phi 2 CT minus 2 plus AT. Now, for this model, when we looked at the AR2 model, we saw that the first autocorrelation is computed as phi 1 divided by 1 minus phi 2. And second autocorrelation is phi 2 plus phi 1 squared over 1 minus phi 2. That's spread in the slides prior to these slides here. Okay. Now, if we computed now the autocorrelation, partial autocorrelation between CT and CT minus 2 given CT minus 1, if you replace what the values for rho 1 and rho 2 is squared, what you would get is that the partial autocorrelation of lag 2 given ZT minus 1 will be equal to phi 2, which is the coefficient for ZT minus 2. Okay. That's the coefficient for ZT minus 2. So that coefficient is measuring how much does ZT depend on ZT minus 2. Given that I already have ZT minus 1 in the model. Okay, so rho 02 given 1 is going to be equal to phi 2. So if it's an AR2 model, then this, if it is in fact an AR2 model, then phi 2 is different from 0, right? Because otherwise it would be an AR1 model. So if it's an AR2 model, then the second partial autocorrelation is different from 0. Okay. Now, what do you think would happen if I were to compute the partial autocorrelation between like ZT and CT minus 3 given CT1 and CT minus 1 and CT minus 2? What do you think this is going to give you? If I compute the partial autocorrelation of CT with CT minus 3 given CT minus 1 and CT minus 2. Okay. So I'm discounted CT minus 1 and CT minus 2. So the autocorrelation between CT and CT minus 3 must be equal to 0?
0.
Right, 0, because I do not have dependency in this equation on CT minus 3. So that ought to be equal to 0. So from this equation here, what we see is the contribution of CT minus 2 to explain CT is measured by the coefficient, okay? Now, by analogy with regression, well, this is occurring because the dependent variable as well as the independent or predictor variables have the same variance. If they had different variances, I could not conclude this thing. And therefore, so I get this expression because the variance is the same for CT minus 1, CT minus 2, and so on. Remember, we assume that we have constant variance. Okay, that's an important assumption here, so that when we standardize and compute rho 02.1, we get that that's equal to phi 2, because we're working with standardized variables. Okay. In regression, when we talk about partial correlations, first we standardize and then we compute the partial correlations in regression. Okay. Now, to simplify the notation, to avoid writing 01.02.1 and so on, we will use the notation phi pi to denote the ith coefficient of an ARP model. Okay, so we will denote by phi sub pi the ith coefficient of an ARP model, so that the partial correlations are going to be given by the succession of values phi jj. Right? That's going to be the partial autocorrelation function. That's going to determine the partial autocorrelation function. These parameters, phi 11, phi 22, phi pp, can be obtained from the Joule-Walker equations, just as we did when before we talked about partial autocorrelations. We saw that the parameters for the autoregressive model could be obtained through the Joule-Walker equations. So the first partial autocorrelation is rho 1, which is the first autocorrelation, lag correlation of lag 1. Phi to 2 is going to be the ratio of these two determinants. Okay, where I have one rho 2 in the diagonal and then rho 1, rho 1. This comes from the Joule-Walker equations. Okay, if you review what the Joule-Walker equations say, this can be derived from the Joule-Walker equations. Then phi 3, which will be the third element of these partial autocorrelations, are going to be the ratio of those two determinants that are there. And you can extend the pattern that this thing follows, and that's essentially phi pp, which will be the pth coefficient of an ARP model. Okay. And the interesting result here is that these partial autocorrelations, phi I, are going to be equal to 0 for I greater than P. So there will be different from 0 up to order lag P, because we have an autoregressive of order P. But beyond P, these partial autocorrelations are going to be equal to 0. So as we saw on the data that we simulated yesterday, when we saw the partial autocorrelations, for an AR2, partial autocorrelations for lags 3 and beyond are 0, the theoretical partial autocorrelations. For an AR3, partial autocorrelations for lags 4 and beyond are going to be equal to 0. So the partial autocorrelation function gives us important information about the order of an autoregressive model. Okay, very important information, because it tells us what's the most likely value of P. Okay, in reality, we never have the theoretical autocorrelation, partial autocorrelation, but based on the sample autocorrelation, we can infer what the right value of P is, because we know that the partial autocorrelation, sample partial autocorrelations, will be statistically not different from 0 for lags greater than P, if P is the order of the model. Okay. Now, of course, in practice, we estimate the correlation, the partial autocorrelations with the sample partial autocorrelations. And to determine if a sample PACF can be considered as 0, we use those bands that you see drawn in the graphs or the partial autocorrelations that we saw that were drawn yesterday in the partial autocorrelation graph, are based on an approximation by Kenwell in 1949, which he made that approximation assuming that if the process is an ARP, if it is an ARP, the sample autocorrelations, then he showed that they are independent with mean and variance given by something approximately equal to 1 over n, where n is the sample size, minus d is the number of differences. Here we haven't introduced the ARIMA models, but in this case, d is the number of differences that we take. D is number of differences. That is when we take the dth difference of a series. We'll talk about this thing later. For now, since we haven't talked about differencing, the variance will be just approximately 1 over n. That will be the variance for I greater than P. Okay, for an AR, given that it's an ARP, an AR process of order P, the variance of the partial autocorrelations will be approximately equal to 1 over n. So the standard deviations will be approximately equal to 1 over square root of n. Okay, and that's how those blue bands are drawn.
What is n? Is the number of like sample, like the
N
size of the sample?
Yes, it's a sample. If I have n observations.
Okay.
Okay, so n is the number of observations. Okay, so that if we can infer that that phi I is different from 0 at the 5% significance level, if the estimate, if the sample partial autocorrelation is outside this interval. Okay, so there is no the distribution, the sample partial autocorrelations, the sampling distribution of those, it's not only that they're independent, but they can be approximated also by a normal distribution. That's how we take 2 times the standard deviation to compute a 95% confidence interval, given that the model is an ARP. Okay, so if it's an AR1, then starting from lag 2 and on, those bands would represent the confidence interval for the partial autocorrelation of lag2, given that it's an AR1 model, okay, and so on. So that's why we use those bands to determine which are the sample partial autocorrelations that are significantly different from zero. Now, this is how the ACF and the PACF behave for an ARP process. This is an ARP process. We saw that the ACF, the autocorrelation function, converges to zero. And we saw last class, when we talked about the autoregressive models, we saw that they converge to zero according to the behavior given by the difference equation that determines the AR model. So the difference equation is phi of B, applying that to rho K equal to zero. That equation determines the behavior of the autocorrelation function. And the partial autocorrelation function for an ARP process, only the first P partial autocorrelations are different from zero. Okay, and that's what's really helpful to identify the order of an autoregressive process. That is what really helps in determining the order of an autoregressive process. Okay. Now, we're going to do one example here. There's three time series that we have here. I will do with you this the annual yield of straw analysis. There are some things that we haven't really digged into, but we'll cover it when we look at the script, and then you'll do the analysis of these two other series. Okay. We're gonna, in particular, let me just make a brief comment here. This chemical concentration series, you're gonna force it to be an AR model. There's a better model than a pure autoregressive model for that series, but we'll make sure that we only fit an AR model. Okay, I'll do the first one, annual yield of straw. So there's a script in Brightspace. It's SD04 that says SD04 AR model construction, annual yield of straw. Okay, so download that script and we'll start working with that process to identify that series and also fit a model. We'll see now how we fit the model, although we haven't talked about estimation, the theory of estimation, which we will be using maximum likelihood. We haven't talked about that yet, but that doesn't prevent us to doing it in ACT, to do the estimation in R now. Okay. So that's SD04, model construction, annual yield of straw is the script. Download it to your computer and install all the libraries. You can read the file.
Yes.
Okay, good. Now let's, you read the file already. I have two columns in the file, the year and the value of the annual yield of straw. I'm going to convert this thing first to a time series. Okay, I have yearly data, so my frequency is 1. I have one observation per year, so I'm just using the function TS with the series ZT annual yield of straw, and I'm calling that ZT because I no longer will need the years, and I'm saying when this starts. Okay, now I plot the series. And there's one thing that you can see here is that there seems to be non-stationarity of the series. Okay, when we talk about the modeling process, we will see that first we need to make sure that if we need to transform the data to stabilize the variance, that's the first thing we need to do. Once we stabilize the variance, then we can work on making the series stationary. So I'm gonna compute here. I have a trend, that's a downward trend, and here's another trend. Okay, so it looks like a polynomial adaptive trend of order 1, right? So I have different intercepts, but I have downward. The slope is probably the same. So I'm gonna try taking the first difference of the series. But before we do that, let's look. I'm using this function ACF2. ACF2 is a function from this package, ASTSA. And this function gives us both the autocorrelation function and the partial autocorrelation function. Okay, we can obtain them just using the default commands of functions in R, which are ACF and PACF. But this one gives us both plots right away. Okay, so I'm going to say ACF2 of the series, and I'm going to put it first. I forgot to change the titles to Spanish, to English, but anyway. So I have ACF. This is the autocorrelation function of the first defect. And I'm sorry about that. I forgot to do something here. This is the original series. I haven't made that a difference. This is the series, right? This is the original series. So this should be annual yield of stroke, because I haven't taken any difference. I'm working still with the original series here. Okay, so the annual yield of stroke, the first one was the plot, and now this is the ACF. Okay, so it looks like it's not dying very fast to zero. I have a couple of spikes here, and there's one significant spike here, whatever. So it may not be dying fast enough. So we will check first if we need to difference it, if we calculate a difference of the series. So I'm going to call ZTD1. I'm going to call that the first difference of the series ZT. Okay, so ZTD1 will have the first difference. And if I plot the series now, I see that now it's stationary. It fluctuates around a constant level. I have some spikes here that seem to be too large, but let's ignore this thing now for the moment. This could be due to some phenomena that occurred in those years. I don't know. But let's look at the autocorrelation function of the first difference of the series. If we look at the autocorrelation function of the first difference of the series, it looks like we have these dies right away. I mean, I have a spike here at lag 11, and that doesn't 11. This is annual data, so this could be due to noise. Okay, we will assume that this is due to noise, and this is this partial autocorrelation function. I can see here that I have only one significant lag in this partial autocorrelation function. Okay. Now let's go back to the previous ACF. This was the ACF of the original series. Now, from this ACF, we can think of this as noise, all this as noise. And I have two significant lags in the partial autocorrelation function. I have two significant lags. Now, that would lead me to think that maybe if this is already stationary, okay, because it dies fast, although it doesn't die exponentially, right? Notice that it doesn't die exponentially. But you may be led to think that we can fit an AR2 model, autoregressive of order 2, because I have two significant spikes in the partial autocorrelation function. Okay. So let's do that. Let's model the original series as a autocorrelation or autoregressive model of order 2. So I'm going to try this thing. Mod 1, I'm fitting the model with the function SARIMA. SARIMA is a function from the ASTSA package that produces the diagnostic plots in automatic. Okay, so that automatically generates the diagnostic plots. We haven't talked about diagnostics, but we will see later that we assume that if the model is right, then the residuals will look like random. Okay, they will be approximately normally distributed, which looks like it's reasonable assumption. This is the normal plot of the residuals. This is the ACF, the autocorrelation of the residuals. Now, one of the assumptions that we will be making is that if the model is right, then my residuals shouldn't be autocorrelated. Okay, that should be taken care of. We'll talk later about this. This is statistic here. This is the Young box test, and the Young box test. What this test does, what this statistic is doing, is testing the hypothesis that the first, for example, here I have lag. This is lag 1, 2. It's a lag 2, 4, 5, something like that. So this one, for example, here it's testing the hypothesis that the first 5 autocorrelations of the residuals are 0 against the alternative that at least one of them is different from 0. So what we want to see is p-values that are large, because that p-values that are large confirm the fact that we do not have autocorrelation in the residuals. We'll talk more about this thing. Okay. Now the other alternative is when we analyze the plot, the ACF of the first difference, we, according to this ACF and partial ACF, this could be a first order model of the first difference of the series. Okay, it could be the first order model of first difference. So we'll try that model. We'll fit now with same function SARIMA. I'll fit a model to the series, but now I'll fit an AR1 model. Okay, an AR1 model, and I will have to add here a 1 because I'm taking a difference of the series. Okay, I'm taking one difference of the series. So this mode 2. Now, I haven't looked at the coefficients here, but I'm focusing on the results of the model. This model, if you look at this model 2, the second model I fit, with one difference, I have several p-values of the Box-Young statistic that are very small, which means that I don't have strong evidence to reject the hypothesis that there is no autocorrelation in the first few residuals. Okay, so this model looks worse than the prior model, because what we want to see in these p-values for the Young box statistics is we want to see high p-values in the Box-Young statistics. Okay, so we would use this model here, mod 1, and here I have the coefficients. Okay, I have the coefficients. AR1 coefficient is significant. Here the p-value is 0.01. We'll talk about how we estimate this, we calculate these p-values and so on later. And the second coefficient is also significant. Okay, the mean is also significant. That means that there is a mean of that to that series. That seems to be a better model. Okay, what if I made a mistake and I fit only I forgot to include the difference here? If I forget to include the difference here and I fit the model, it still looks bad. Okay, we have many p-values of the Young box statistics are very low, are less than 0.05. Let's say the boundary here is set at 0.05 to test at the 5% significance level. And we also appreciate some trend in the residuals. Okay, here I have a trend. I shouldn't be able to see trends in my residuals. Okay, so again, this is not a good model. And if we look at the coefficients here, there's only one coefficient significant, but my residuals, my diagnostics tell me that it's not a good model. Okay, So even though we haven't gone through many processes of identification or identifying a model and fitting it, I'm going to ask you to work with, all you need is this script. Based on this script, I will ask you to fit the models that are in the presentation, which is the chemical concentration file and the USGMP and chemical concentration. Okay, so I'll divide you in groups. Okay. And I will enable everybody to share. And we'll give probably 10, 20 minutes for you to finish. Although it's very quick exercise. I'll give you 20 minutes, okay? So I'll create the rooms. Any questions before I separate the rooms?